For example 2 here in the chapter on transfer functions, we're now given a third order system, and we have input on the right side in terms of u and the time derivative of u. And we want to do kind of the same thing we did for example 1. We want to know the transfer function, we want to know the poles and zeros of the transfer function, and to characterize the free response of the system. So here I took a Laplace transform of our equation of motion. I got this. And I said that since we're looking for a transfer function, we're really looking for forced response. Forced response means zero initial conditions. So from that, I solve for the transformed response there, y. We see again, it's as expected, the ratio of n over d. And then from that, we can find out our zeros and poles. Well, these zeros are the value of s that make n a zero. So we have one of those roots. So z1 in this case is equal to 2/3. The denominator d produces for us our poles. We find the roots of that. And what I did was I factored the cubic equation into a product here of a linear and a quadratic factor. So from that we can see that the first pole is going to be when s is equal to a 2. And then we have the quadratic, which is going to give us poles 2 and 3. So that's going to be minus 12 plus or minus 12 squared minus 4 times 61 divided by 2. And you carry this out, you get a minus 6 and plus minus 5j. So our poles are 1 real and 2 complex. They're complex conjugates. That's no surprise, because that's what you'll always get back from your real denominator of d. And importantly, they have negative real parts. Now, in terms of the free response, what I should have done from the beginning was put my initial conditions in there, but I didn't. So let's go back and now Laplace transform our equation of motion for the case of zero input, since we're looking for free response. So Laplace transforming that equation of motion, my terms involving the transformed response y, there's going to be an s cubed, there will be a 10s squared plus 37s minus 122 times not d but y. And then I'm going to group all my initial conditions together. From the cubic term, I'm going to get an s squared initial condition on y. I'll have an s times initial condition on y dot, and a y double dot initial value. Then from the second term on the left side, I'm going to get a, I can't leave off my 10 here, minus 10, and that's an s times initial condition on y plus a y dot. And then the last term, the minus 37 times the initial condition on y. Again, the minus signs are all coming about here because that's the sign that always appears in front of your initial condition terms on whatever nth order derivative that you've got. Since we're looking for for free response, 0 input. We have a 0 there on the right hand side. So therefore, the transform form of our free response is going to be, if I write this out in factors of s, I'll have an s squared times the initial value for y. I'm going to have a y dot initial condition. I'm going to have a 10 times the initial condition on y, all times s. And then for the constant term in that, I have the initial condition on y double dot. I have 10 times the initial condition on y dot, and 37 initial condition on y, all divided by d. And d, again, just to repeat that, is s cubed plus 10s squared plus 37s minus 122. And we already know a lot about d because we know its three roots, it's the three poles of the problem. To put it in the notation of class, I'll just call the top part f, and then the factored form of d is s minus p1, s minus p2, s minus p3. So, we know we have distinct roots. One is real, the other two are complex conjugates. So I just write them down as a1 divided by s minus p1, of a2 divided by s minus p2, a3 divided by s minus p3. And reminder here that P1, what did we find there for P1? That was a 2. And P2 is equal to minus 6 plus 5j. That's the name I'm giving that. And P3 was that. Again, the basis for being able to write down this is simply that they're non-repeated, they are distinct roots. But the virtue of the fact that P3 is actually equal to the complex conjugate of P3. P3 is a complex conjugate of P2. I can rewrite this thing here as the complex conjugate of A3 divided by A2, S minus P2 complex conjugate. As that. And from what we have talked about before, that when you add together two complex numbers who are complex conjugates of each other, it's 2 times the real part. In this case, I'm going to write as A2 over S minus P2, like that. Again, that's only just a virtue of adding together two complex conjugates together to get twice the real part. So we're in a position, therefore, of knowing that the free response we do the inverse Laplace of each one. I've got an A1E P1t, which was a 2t. I have 2 up here, and then the real part of the exponential gets brought to the outside, so that's an e to the minus 6t, and we'll get some coefficient a. You can do the algebra to find out what that is, cosine 5t, and another coefficient b from which you can solve or do your algebra to find that, and you get that. So again, we didn't really do all the work. We didn't bother to find the residues of A1 and didn't write down the algebra that goes to find what exact numbers you get for A and B, but we didn't care about that. We're only looking for the character of the response. This part here is going to be a growing exponential. This is the one that will dominate for a long time, because this term, set of terms here, is going to be decaying exponential times harmonic. For a long time, the harmonic doesn't really make any difference because that will wipe out that with time. So our dominant part of the response is that. So we went through some of the work that takes us down to that step, but what we need to learn to do is that we don't even have to take it this far. Once you know the poles of your transfer function, that's all you need to know. Because right here we could have said, well, based on what we've seen before, when your response or when your poles are complex with with negative real parts, that corresponds to decaying exponentials. And since we have a real positive pole, we have an exponential part of our solution that actually grows with time. So again, all this down here was just to help make the point. With experience, we can draw that conclusion right away, just if we know the transfer function and then know the poles of the transfer function.